Looking up at a star-filled sky, you are seeing light that has traveled across the vast gulf of space for dozens, hundreds, or in some cases, maybe even 1,000 years or more, before finally reaching your eye. The light from the sun that we see around us on a daily basis, well, that light left the sun's so-called surface a little over 8 minutes and 20 seconds ago. But the truth is, that light has actually had a much longer travel time than that. Hello everyone, I'm Daryl Heath, NASA Outreach Coordinator for the Arkansas Space Grant Consortium based here at UA Little Rock. Welcome to the night sky. Located approximately 93 million miles away from Earth is a power plant capable of producing a colossal amount of energy. At any given moment, it generates something on the order of 350 billion megawatts in the form of light and other forms of radiation. Of course, I'm talking about the sun, the closest star to the planet Earth. Like any star, the sun is a seething mass of churning plasma. Plasma being the fourth state of matter. The other three include solids, liquids, and gases. But if you heat a gas high enough, it becomes so hot that the atoms comprising it break apart into a soup of charged particles, plasma. In many ways, the sun is a rather average star and is made up primarily of hydrogen and helium, with a smattering of other elements. It's the source for virtually all of our heat and energy needs, and it's what makes life on Earth possible. In order to generate all of those megawatts, the sun must have fuel, and hydrogen is the main fuel source for the sun and all other stars too. Deep within the sun's core, where temperatures and pressures are so extreme, nuclear fusion can take place. Every second of every day, the sun fuses 700 million tons of hydrogen into 695 million tons of the heavier element helium. That missing 5 million tons of matter, turns out it's not really missing at all. It gets converted directly into energy, light and heat, as per Albert Einstein's equation of E equals mc squared. The sun has been doing this for the better part of its 4.5 billion years of existence, and it'll continue to do so for several billion more. Bottom line, all the stars that you see shining in the night sky do so because of nuclear fusion. Before we go any further though, I want you to keep in mind that visible light is only a thin sliver of a full range of the same phenomena that we call the electromagnetic spectrum. Whether light is visible or invisible to our eyes depends on its wavelength, and the spectrum runs from short wavelength X-rays and gamma rays that have wavelengths around a trillionth of an inch to radio waves that can have wavelengths anywhere from a millimeter to around 100 kilometers. Visible light has a wavelength that ranges from around 400 to 700 nanometers. 1 nanometer is equal to a billionth of a meter. However, the sun produces light all across the electromagnetic spectrum, everything from deadly high-energy X-rays and gamma rays to ultraviolet light to visible light and all the way down to infrared, microwave, and radio waves. But no matter what part of the electromagnetic spectrum we're talking about, the fastest possible speed of any form of light is always 186,000 miles per second, the universal speed limit. You should also know that light possesses a dual nature. It can behave as though it were a wave, but at times it can also behave as though it were a particle. These tiny particles of light have no mass and exist as discrete packets of energy that we call photons. This is true no matter which part of the electromagnetic spectrum we're talking about. I mentioned earlier that 8 minutes and 20 seconds is the travel time for a photon leaving the sun's surface and finally reaching the Earth. But now let's dive deep into the sun's interior to see just how long it really takes for a single photon to work its way out before embarking upon that journey. It's only inside the sun's core where nuclear fusion can take place. Normally, the protons of hydrogen atoms tend to repel one another because they all carry the same positive charge. So it takes some really extreme conditions in order to get them to fuse, and the interiors of stars, with their extremes of pressure and temperatures, permit this to happen. Recall that the sun's heat breaks up atoms to form a state of matter called plasma. In the core, temperatures reach 27 million degrees Fahrenheit. Under these conditions, hydrogen atoms are broken up into their constituent protons and electrons. The nuclear fusion process is a bit complicated, but in the Sun and other stars it ultimately boils down, no pun intended, to taking 4 hydrogen protons and then fusing them together in order to make the slightly heavier element helium. A small portion of the mass produced by this fusion process is converted to energy in the form of gamma-ray photons. Remember, gamma rays are very high energy, and if that's what the Sun emitted as light, life on Earth would not be possible. So yeah, it'd be great if the Sun found a way to tone all that down a notch or two, and thankfully it does. If that gamma-ray photon had a clear shot all the way to the Sun's surface, it would be free in just 2.3 seconds. But that isn't the case. By most estimates, the density of the Sun's core only allows it to travel less than a millimeter before it collides with another particle, each time getting redirected as it does so. This leads to what's commonly called the random walk. In each step that photon takes, it is constantly being sent off in a random direction after bouncing into other particles. Some of those steps might take it in the direction of freedom, while others might just as easily send it right back where it started from. It's not easy to give an accurate time frame for the photon's escape from the core, but at a minimum, it could take many thousands of years. But once it does, its journey is not over. After finally breaking free of the core, our gamma-ray photon now enters into a layer of the Sun known as the radiative zone, which stretches from the outer edge of the core to about 70% of the Sun's radius. Moving away from the core, the density and the temperature of the Sun's plasma slowly dissipates. At the edge of the core, temperatures are still right around 27 million degrees Fahrenheit, but finally cool to around 3 million degrees Fahrenheit at the outer edge of the radiative zone. In the radiative zone, energy gets transferred by means of a game of hot potato. As photons continue to collide with atoms, still getting redirected, they also lose a little bit of their energy. The atoms they collide with absorb some of the photon's energy, become excited, and then release it again so that it gets absorbed by other atoms, each time with a little less energy than before. So we start out with gamma rays, move on down to X-rays as the photons work their way towards becoming photons of visible light. After many thousands of years, our photon enters into the Sun's convective zone. Here, in the remaining 30% of the Sun's radius, our still highly energetic photon heats up the plasma to the point where convection currents are created. Just like a pot of boiling water, blobs of hot plasma rise up towards the surface, where the plasma is less dense and temperatures are relatively cooler. At the outer surface of the convective zone, the plasma density has now dropped to 1,000 times less dense than air, and our little photon has finally shifted into the visible part of the light spectrum. It's now free to leave the Sun from a region that astronomers refer to as the photosphere. Depending on who does the calculations and the measurements of density that they are using, our photon has taken a journey of 100,000 to 1 million years before finally escaping into space. The Sun releases about 10 to the 45th power photons, and that's a 10 followed by 45 zeros from its surface every second of every day. Some of those photons will shine on alien worlds, such as the surfaces of the moon and planets, so that we can see them shining in our night sky. Some will careen off into places beyond our solar system, and some of them will reach the planet Earth where they might be absorbed by green plants, which use the photon's energy to make chemical energy, the ultimate source of our food and fossil fuel energy. Still others will enter into your eye, ping into your retina, trigger a cone cell, which then sends a signal to your brain that gets interpreted as an image. There, you'll perhaps form a memory of a warm summer's day, of the dappled light of sunshine on the surface of a lake, the riot of colors in a field of wild flowers, or the beauty of a child's smile. That million-year journey of a photon has then reached its end. NASA currently has 2 robotic spacecraft studying the Sun. SOHO, the Solar and Heliospheric Observatory, is the longest-lived solar probe yet, having launched in 1995. It carries 12 scientific instruments to study the solar atmosphere, helioseismology, and the solar wind. Information from the mission has allowed scientists to learn more about the Sun's internal structure and dynamics, the chromosphere, the corona, and the solar particles. The Parker Solar Probe is the newest of NASA's solar explorers, having launched in 2018. The spacecraft is on a mission to touch the sun. The spacecraft is flying closer to the sun's surface than any spacecraft before it. The mission will revolutionize our understanding of the sun. Parker will fly more than 7 times closer to the sun than any spacecraft. Over 7 years, the spacecraft will complete 24 orbits around the sun. At its closest approach, the spacecraft will come within 3.9 million miles of the sun. That's all for now. I hope that you have a newfound appreciation for sunshine. I also hope that all your memories are pleasant ones, and that whenever you look up into the day or night sky, that you continue to do so in both awe and wonder.